Hello, everyone. My name is Nathan, otherwise known as Old Man Builds, and I wanted to talk to you guys today a little bit in physics. We're gonna talk about some energy here. Now, usually when we start talking volts and amps, I try to tell people that the heat is involved in the equation. So whether there's lack of heat, whether there's heat in it, it's going to change everything. So here's the thing. I think physics got this wrong when they tried to put it out there. They tried to make counterspace something that it isn't. They tried to make it something that they can just put a letter in the place of. What's the problem? It's actually a temperature differential in what they're doing. So when you want more amps, you're going to get more heat. We all pretty much know that, right? But do you know that it also lowers the frequency? So say that I want less amps. So I'm going to bring up the volts. Well, I'm also going to bring up the frequency when I do that. And it's going to cause cooling once you're in the amp stage and then you go to the volt stage, it'll cause it to cool down. So why is this so difficult? We all see it in our projects, but the problem is when it comes to physics, it's broken because they like counter space, but they have it in a math equation and it doesn't belong there. So when I looked at it, I tried to figure out why everybody in the world doesn't understand this. So if I have an amp motor, what do I need to do? I simply need to cool it down in order to get the volts out of it or change the frequency. That's it. If it's that simple, okay, all we have to do is really just come to the understanding that that has to change. That if we understand it correctly, we're going to get the right result. So one of the biggest things when we do this is that we wanted to look at how we fix something. And I do a lot of mechanical work. When you actually want this to work for you, you have to understand it. Now, when I switch things around, I don't just do it because I do it because I understand it because I need a certain result. So let me bring up Eric Dollard. Let me just show you what I was looking at yesterday is the reason why people do not understand this. So let me show it to you right now. Here he is. And I'll hit play on this. Make sure the volume's up.
I would love to see a snack project.
So at any rate, so what we're talking about is electricity. Let me change colors here. Maybe this one will erase easier. I'll draw lighter. Okay, so let's come up with a dynamical situation that everybody can relate to because they all drive. Everybody here drives an automobile or has been in one. So what we're going to do is we're going to use that as our model. Okay, and we're going to analyze it dynamically just as we would all these electrical things I'm talking about. Okay, so now what we decide to do, okay, is if we're moving at a speed, okay, and then all of a sudden we decide we're going to go to another speed. Okay, and then stop. Now all kinds of things happen when we do this. During this interval of time here, things happen that are measurable. Okay, now if the speed increases at a constant rate, what we get is we have a force pushing us, okay, which all of a sudden becomes a constant force, okay, pushing back. And then when the speed change is over and we're at a steady speed, this force disappears and then there's no more perception of movement. Now another thing happens. If we measure the quantity of gasoline in the gas tank, okay, and there's 100 cubic centimeters before we start, and there's 50 cubic centimeters after we execute this function, then not only do we have this wave in time, but now we have this little cube in space of gasoline that doesn't exist anymore. No.
And there it is. Right when he starts saying, we have a cube in space that doesn't exist anymore. That's what they call counter space. It's a humongous flaw. It doesn't belong there. What belongs there is the true understanding of a temperature transference. You basically have to transfer your energy into temperature difference. That's what's going on here. We're not having a liquid. We don't need to apply the understanding of a liquid here because it's a false understanding. You don't want that understanding because you're looking for a volume of something, of a liquid, which does not exist there. Energy's different. Energy transforms. It doesn't just stay in a linear path. It'll transfer into heat. It'll transfer into frequency. This is also why Tesla is so misunderstood, because he does a lot in frequency. So when we start looking at this, we need to change how we think. There's also another major flaw in here. And I'll just show you. We'll bring this back up. Look already. We have a PWM signal. Now, I know a lot of you out there look at that and go, well, that's right. We've seen that a million times. What's the problem? Well, the biggest problem with this is that energy doesn't run on the wire. So when we see this, maybe it's just the way we think about it. We automatically think that the energy is running on the wire, and then they give a signal to it so it goes off the wire and comes back. That's wrong. And I'll show you right now. I'll pull this up. And it's actually opposite. So now that we look at this, you see the correct way to do it. When you turn DC voltage on, it's at the top. When you add a pulse to it, it's pinching. So when you see the little wire there that I drew, right? And you start to see that the energy's there. You see the big donut on there and you go, okay, what happens now when I hit the PWM? Well, I'm pinching it. Now, how does this make sense? Because every time I pinch it, I'm adding heat to the system. I'm forcing everything to come together and push upon it. Now I'm slowly pushing it together and I'm creating a spot where it can't get through as much. So I'm basically creating a ton of heat in that one area. So what does that mean when I create a ton of heat? My amps rise, my frequency goes down, okay? That's what's going on here. So the voltage that transfers on the outside of the wire and it goes down and we pinch it, that means that I'm hitting my signal right there. Now I'm creating heat in the system. Now when I let it go, the opposite happens. I'm releasing the heat and now it's able to flow again. So what happens? Now it goes back to the top thing it's on. This is the thing here. We don't understand that the voltage is passing on the outside of the wire, not the inside. The amps are more what's in the inside. However, you cannot get a magnetic field without both of them. Now, this is why you sit there and you look at these things and go, oh, well, now it starts to make sense, right? And you go, why would I want the voltage not to go up like that? Well, because it doesn't do that. You're removing something. By pushing it down and forcing, you're condensing the energy. You're removing something. Okay, you're pulling the field in. When you pull the field in, you get heat, you get amps, you get more. Okay, when you push it back out, it's a duty cycle. You get it to pull back out. You get it to cool down. That's the understanding here. So when we do this right, now physics has to change. Now it cannot stay the same. When we talk about counterspace in this, now we know it's a temperature differential. We know it's not supposed to be that way in the way that they see it. When they see this, they think, oh my God, I could just go over and put anything I want in there, it'll be okay. But the problem is you can't, because the energy isn't disappearing. It's just transferring into heat. Then it transfers back into the energy. That's it. it's not a loss. So you go, well, how about hysteresis? Can we use hysteresis to define this? Hysteresis is usually energy loss. It's explaining why you have loss in a system. It's not so much explaining that energy comes back as the same thing. It's coming out as energy loss. You are losing energy in a system. That's why they put it in there. That's why Steinmetz turned around and said, okay, we need to account for the loss in the system so that we can fix the system. Okay, well, that's hysteresis. Now, you want to do the opposite of that. You want to keep the system together where you're not losing the energy. Therefore, you have to come up with a temperature transference. You can transfer the heat, okay, as the amps into voltage. What does this mean? Basically, when you start to look at different motors and you want to run an amp motor, what do you have to do to get the voltage out of it? See, a lot of people won't understand that. You have this amp motor and you're thinking, oh man, well, it's useless because it only gives me amps and I'm not getting a whole lot of volts out of it. How do I get the volts to make it useful? Well, if you understand temperature transference, then all you have to do is put the duty cycle in there in order to cool it enough to get the amps out of it. That's it. That's the difference between a productive motor and a non-productive motor. You just had to understand what you were dealing with. Now, if you don't, all you're going to get is amps out of that motor and it's going to become completely useless to you. Okay? It is ruining your experiment not knowing this. So you go, oh my God, but I have counterspace. So let me see, you're adding a value of liquid that doesn't belong. There's no liquid in the system. There's no compression of it. There's no loss of it. No, it's a temperature differential. You're changing the temperature in the system. So you're changing how the energy is going out. Now, why do I say there's no loss in it? Well, you're not turning off the voltage. So as far as you know, there's no loss in it. Is there an actual loss when you have heat? Yeah, there is. And that's where hysteresis comes in because it deals with the loss of it, right? But we're not talking about that. We're talking about a system where we're just transferring between amps and volts. And that's all we want to do here. So if you take high voltage, right? And you want to bring up the voltage. It's real simple. They do it all the time. They take a flyback transformer and basically they take a magnetic core, and in that magnetic core it puts out a field. Then it goes through several diodes, and then the diode on the last side will actually make it into higher volts and lower the amperage. What is it also doing? It's raising your frequency. It's really that simple. Then we come around and we want to do the opposite. We want to cool it. Now I'm just going to take a duty cycle. And all I'm going to do is I'm going to pulse that duty cycle. And when I do, I pinch the wire. So what am I doing? As it's unpinched every time, it cools. When it's pinched, it heats. So by doing the unpinching of it, I'm reducing the amount of heat in it. Therefore, I can now get volts out of it instead of just amps. That's about as easy as it gets. So you want to do this experiment, right? And you want to verify it. So let's verify it. Let's just do that. Let's pull up another video because we want to make sure we got it right. So I showed this a lot. And hopefully you guys understand it now that I explained it.
To this guy, I'll leave a link in the description so you can go ahead and subscribe to him, guys. He's got some amazing stuff coming out. And I hope you enjoyed this video of the validation that he did.
Hey, hope everyone's good. This is a video in response to Old Man Builds. Nathan's got a good point there. So let's take a look at what we've got going on here. So cruise over here, right? So you notice what's happening here, right? You see how the frequency is changing, right? We have response there. Now let's look over here, right? So we initially dialed it up to 12 volts, but you can see we're just under 4 amps of draw, right? So when we actually change the pulse width, check this out. See that? See how the amps start dropping and the voltage rises, right? It's an inversion. All right, we'll go the other way. Notice the amps are rising, voltage is dropping, right? There's your duty cycle action. I haven't adjusted the voltage at all, okay? Now when we look at the frequency, what happens this time, right? As I go up in frequency, the amperage drawn goes down, right? And there it is. You hear that? That's what we're talking about right there. He's totally right. There's a 5-to-1, okay? As we know, everything is connected. You know, you can't just change one thing and expect to get something, you know, isolated. Everything changes and moves with it. All right, so we're also looking at the actual resonant frequency of the flyback system itself, right? So I'm changing the pulse width. You notice we've dropped in voltage, right? There's a raise in amperage, pulse width down, right? Raise in voltage, drop in amperage. See that? Now we're increasing the frequency. Now we're decreasing the frequency. Now you hear that, right? So we're coming out of the ultrasonic range. Right, and this has a lot to do with the resonant frequency of our flyback, right? So everyone's slightly different. You got to kind of find your zone. So look where we're at right now. 8 grand. Right, let's take it all the way. Right. So you see that now we're way high on the amperage, right? We'll change the pulse width. Yep, wrong way, right? See that? Lowering of amperage, raising of voltage. Right? You can hear it kind of slowing down.
All right, I'm going to pause it right there. So what did we just see? It's extremely simple. All we have to do is raise the frequency in order to raise the voltage. Then it lowers the amps. That sounds pretty simple. We can all go with that, right? Now, what if I want more amps? I simply lower the frequency and I change the duty cycle. Then I get more amps. That's it. That's the whole temperature transference. Why is this a mistake in physics, though? Because when you apply the wrong law or you apply something that doesn't belong, it takes everybody's whole experiment out of whack. So when they start applying this and say, I'm going to take a B and put it in the place of the temperature transference, well, then the whole result is garbage. You might as well throw that whole paper in the trash. Take that whole experiment and stop right there, because you're not getting the right answer. You're not ever going to get the right answer that way. The way you have to do it is by what it's doing, not what you want it to do. You have to follow what it's doing in order to manipulate to get what you want in the end. But if you don't understand it at the beginning, it's a complete failure. Let's go back to Dollard now. Let's take a look at this some more and what he has to say.
In other words, we have this force that appeared and disappeared, and we have 50 cubic centimeters of gasoline that went somewhere and is gone. Now, this is what's called differentiation and integration. This is calculus. Okay, this is how Newton and Leibniz and these people, they wanted to find the relationships between these situations of why you have this integrated situation where you have the accumulation. In other words, the gasoline just doesn't disappear at once. but it accumulates or deaccumulates. In other words, it's an averaging process that weighs something that you can hold on to. Now we have this time differential here, which is kind of abstract. It's like only there when we're changing velocity, and then it's gone. So now if we take the weight of your body, okay, and we symbolize it by the Greek letter phi, okay? Now we take this, you put a scale against your back in the seat, and we take that, okay, and we symbolize that by the Roman letter E, okay? And we take this interval of time here, and we call that T. So this is the weight of your body, okay? This is how much perpendicular weight there is pushing back on the seat. In other words, the reactionary weight, and this is the time in which this happens. Well, lo and behold, then we have a situation where we've analyzed algebraically what's going on with a very simple mathematical ratio. In other words, your weight as a ratio to the time involved in changing your velocity gives you a force E. Now, what I can do without any changes at all is this Greek letter phi represents a quantity of magnetism. Okay, the time T represents the change in that quantity of magnetism, whether I'm turning the current up or I'm turning the current down or the magnet's moving or whatever. And that gives me what's called the electromotive force E. So now everybody here understands Faraday's law.
So now let's understand something. We now have something in place of what we need to. He knows it. He's seen it in the lab. He's describing it in what he's saying. He knows that there's a temperature transference going on. He knows exactly what's going on. But the way that the physics is describing it with counterspace, it makes it wrong. See, a lot of good experimenters already know how to fix this, but not a lot of people understand it beyond that, so they get to write papers about a whole bunch of garbage that doesn't make any sense because it's not based in reality. That's the problem here. That's what I'm trying to get at. Now, I have no problem with the rest of it, okay? I just have a problem with the fact that you're putting in some form of a letter where you need a variable understanding here. And it's going to change every time you change your system based on the numbers that you put in. So you have more math to do. Unfortunately, that is the case. You're going to have to do that math to get the right answer. You can't just put one number in there. I cannot substitute B for what it's supposed to be. I need to put in the correct equation. That's why this is making such a big difference. It ruins physics experiments. You cannot give these people a license to continuously change things because they will try to change everything. And that's the problem. It just doesn't work that way. It's fundamentally unsound. This is why I have a problem with it. All I want them to do is to understand the energy isn't going somewhere. It's just transferring. We're transferring into heat when we transfer it into amps. When we do the duty cycle, we're transferring back into voltage. Now we're able to pull this thing apart and push it back together without the loss. That's the understanding here. That's what I don't think a lot of people get. So now that we do understand it, now your experiment's going to be successful. Now I can turn around and I could take that amp motor. I can now get voltage out of it. All I need to do is create the process to do it, but I have it. I know it's possible. It's just filtering it. That's all there is to it. All you have to do is change it. There's not a whole lot else that's going on here. Dollard knew it. Oh, he knew it big time. As soon as she said it, he was saying that there's something going on here. Okay? It just doesn't disappear. You can't take a quantitative measure of a liquid and apply it to energy. Energy doesn't work in that way. It doesn't have the volume that this does. It's in a different volume. Its volume comes out in temperature. That's the difference. Now that you have it in the right state, Now you can understand it. You cannot apply volumes of liquid or volumes of mass to this. It's the wrong equation. You have to apply temperature transference to it in order to get it right. Once you get it right, continue with your experiment, continue with the math that they have, because then you'll be on the right path. That's all I'm trying to say here. So I just want everybody to start understanding, if you do this, now we could take some cool motors that are out there that are all amps, we can get the voltage out of them fairly quickly. Now you say, okay, well, it doesn't take a whole lot to run a motor like that. I believe it was Faraday that came out with the amp motor. So you go, okay, now instead of a motor that doesn't work, now I have something beautiful. Now I have something that I can pull the amps and transfer in some of them into volts. Now I got something. All I got to do is cool a little bit and lower the frequency. That's it. That's all you had to do to that system to get the volts out of it. Now we have a productive motor. What's great about the motor? The amount of energy it takes to turn it is very little. So now you come over here with the little RC motor and you're spinning this shaft with a magnet, being that it can do it. If you have enough torque in it, then guess what? I spent 12 volts to do it and I got what? 1,000 amps out of it? I'm rich. I have the greatest thing on earth. Now, all I got to do is transfer the energy. All I have to do is duty cycle and frequency change this thing, and I have it. I now have a useful volts and amps. That's why it's so important. It's like giving the keys to the castle to somebody. It's like getting something right when it's always wrong. You cannot apply volumes of liquid to things. So we have to go back to where they started and look at, hey, did they apply the correct thing to this formula? And then get it right. So, like I said earlier, hysteresis deals mostly with the loss. We're not dealing with the loss. We're dealing with the transference. We're just transferring energy. So I hope people really start to understand this, take it in their mind, and start to really get what we're trying to do here. We don't want to live in their system where we're wasting the energy. So just a little side note here so you guys understand this. What was going on with the energy? Well, they dumped a lot of it. There were spikes in the energy, so they dumped it. They didn't want that. There was heat going on. They allowed so much heat to be in there. Steinmetz left it in there. He just got it to the point where it run. What did we not do? Well, we didn't go back and look at the system and say, you know what? Maybe we should make it more efficient. Yeah. Hey, hello. There's an idea right there. From Steinmetz day till now, 10% efficiency gain. That's it. Why? Why wouldn't we get more at this point? I mean, it's just ridiculous. All you have to do is understand this. So if you put a gigantic piece of block of iron around this thing, what's going to happen? The heat's going to get in it. It's going to get trapped. All it's going to do is heat up. You're going to get energy losses in the heat because it's retaining the heat. It's not going back into the system. It's now in energy retention mode. It's taking it, and then as it gets to the cool air, it starts to dissipate the heat. But when it's dissipating the heat, it goes out as a loss. That's the problem. So you go, well, do you need iron in there? Yeah, you do. You want a magnetic field. You don't want such of a magnetic field. You don't need to overpower the system and get a great loss. You need to get it right. You need to start putting in the correct amounts. Now, there's alternative materials out there. We don't need soft iron all the time. You could do it with other materials and you can create it better. That's how you start to make gains in this. You want as much energy as possible. What is the key that Tesla brought into this that people don't understand? It's the resonance. We do not resonate our motors according to what is resonating right outside our house on those towers. Okay? We're not resonating the same. So when you want to resonate it, what do? You basically take your transformer that's outside, find the frequency, and resonate to that. What's the efficiency do? It goes up 15, 20, 30%. It goes up. So what's the biggest problem with that? Is that you're going to get runaway resonance. And what that is energy will continue to build in your motor and you can't get rid of it. That's why they do not resonate them at the same frequency. You see, when you resonate something at the same frequency, you're going to get a change in the resonance value. It's going to lower. So if you say, this is at 300 kilohertz and I'm going to resonate this at 300 kilohertz, when you match them the same, they drop down to 260 kilohertz. That's how you know you're in resonance. It's a fairly simple and easy way to do it. Why are we not getting closer to the transformer frequency? That's what I want to know. There's a certain range in which it works. And that kind of tells you the whole story here. You are getting some of the energy. You're not getting all of it. It's not efficient. It's just enough in there to make it work, but it'll also heat up your system. Then you get the law of hysteresis kick in. That's the problem, isn't it? You just got to be able to work these things out. Resonate your transformer. Okay? If you can take a tuning fork and turn on a transformer, then you understand what you're doing. Okay? It's not that hard. Wrap it, check the frequency, see that it comes out to be 432 hertz. And then take your tuning fork and it'll turn it on. You'll get energy out of it. Then you'll start to understand this process. Tune with your transformer. Get it close. Don't go exactly the same. You're not looking for a complete resonance. You're looking for the sympathetic resonance out of it. You're trying to get close to the value without hitting it because you do not want to get a runaway resonance, which will just continue to build and build and build energy. That sounds so great. The problem is it's going to destroy everything. Okay, you're going to be taking baseball bats to your project in order to get it to stop. That's not good. So there was something else in here I wanted to talk about so that we can understand, but I'm going to check the chat real quick and see what we got. Very interesting. There's a waste of heat. Yeah, it shouldn't. Okay. Yeah. You could get this thing down. Yeah, quite a bit. Tank circuit. Yeah, you know what? Right now, that tank circuit's going to become a very big thing to look at, guys. Just so you guys understand this. Sean's working on a tank circuit on a Tesla coil. And let me tell you, there's a whole lot of big changes coming in your Tesla coil and what we're going to start to actually do with this stuff. And I'm going to go ahead and I'm going to try to find the spot here where Dollar talks about this. Because Tesla created something that everybody needs to understand. Okay? It is that big of a deal. And he was tapping the ether to do it. It's one of the things that are lost in his notes. And you're only going to find it if you actually experimented. I found it. So let me go ahead and pull that up. I'll try to find the right spot real quick. And man, is it going to make all the difference in the world.
So what Tesla did is he had figured out the frequency of the Earth, or the harmonic that he could use, which he started working at about 80 kilocycles, and eventually he worked his way down pretty close to 50 before the thing was all tuned up. It was a transformer that had a coil 50 feet in diameter. The output terminal of the thing was on 100 and something foot, at least 100 and something foot mast. And the idea was Tesla was going to send an electrical pulse into the Earth. It would bounce off the inside of the Earth and come back at a certain time with a certain increase or decrease in energy level. And he was going to continue this process, in microsecond groups as these 50 kilocycle waves are echoing in the planet until what he would produce, it would be a giant electrical fountain of the Earth's activity. at that point in Colorado, which is kind of a place where it was safe to blast because nobody would get hurt. The elevation was good, and this is the place he chose to do it. So when Tesla closed the switch, after all the experiments and tests, he produced for a period of about maybe 1 minute a standing lightning bolt at the terminal of his giant transformer in the building that contained it. Not just one pop, almost standing lightning bolt, modulated at about 5,000 cycles a second from his capacitor discharge switch. So the sound must have been something that was unfathomable to describe. Tesla succeeded in concentrating the entire electrical activity of the Earth into his station in Colorado. So he packed up his bags and moved back to New York, and Long Island began to build the final station where this was not an experiment. It was something that worked. So he could start applying it to electrical transmission. Well, yeah. Okay.
Sorry. Just out of curiosity, are you going to comment on the spatial tether experiment? In more recent times, it's a kind of reflection on this idea.
Which experiments now?
The tether experiment, where they towed a line behind the spatial and collected this enormous amount of current.
No, basically this whole discussion ends with the death of Steinmetz.
Okay, but I just thought it was like interesting.
Well, I mean, yeah, there's some other, but later on, I mean, if anybody's got anything to add with any newer experiments but right now I'm taking everybody back to the 1800s. Yeah. We don't even know what the space shuttle is. The whole idea is to recreate the mind of the people that invented all of this. Is what I'm trying to do, and then each person can fit it into their own analogous business or understanding or whatever. So, but I still got time. Things can go in any direction. So right now, I just want to introduce the characters.
You need to go. What time is it?
I sent you a text earlier.
Okay, so are we back on?
Okay.
Well, okay. So Tesla basically,
at 12.
This was about 1903. Around then, Tesla was promptly put out of business. And as far as overall history goes, he spent the rest of his time as a homeless person, feeding pigeons on the street. And all the rich people that he made rich and all that, basically just always made sure he had a place to take a shower or a hotel room. So the world's greatest electrical genius spent nearly the entirety of his adult life feeding pigeons on the street in New York City and hanging out in the library. So that's the end of Tesla. But we still got Steinmetz. Okay, now Steinmetz has taken the heaviside mathematics.
Okay, so I must be on the wrong page here. Here's what I'm getting at, okay, with the Tesla thing. I wanted to show you something, and I don't think they covered it right there. As a matter of fact, I know they didn't. So I hit the wrong spot of it. This right here. How many people know this? When you start putting a rod down the center of your Tesla coil, what happens? Does anybody know? Well, one of the things that starts to happen, so we all understand this, is you pull a different energy. The energy that comes out of it is now cold. It's also safe to touch. That's one of the things that's going on here. You're producing a different energy. You say, a lot of people look at Tesla and they go, well, he tried to create energy in the air. And you fly by in your great weather ship, right? And in this weather ship, you can get all the energy you want. Well, that's not what his test did. That's not what he did in Colorado. What did he do? He put the light bulbs in the ground. He just walked away from the Tesla coil and started putting light bulbs in the ground. That's why he put the rod down the center of his Tesla coil. He now transferred the energy into the ground. But the fact that it wasn't producing a bad energy when it came down from that shaft is really what you need to understand. He's putting energy into the ground and electrifying it with energy that doesn't kill people. That's kind of one of the things right there. You have to put that rod down the center of that Tesla coil into the ground. Hit the water table. You're going to use the water as a ground. Why? Because it flows everywhere. Now you're having energy transference through the water. You now can put out a giant field into the ground and stick a light bulb where you want. Go a distance away, put it in the ground. Go a distance away, about a mile, put it in the ground. Why do you think he was putting light bulbs in the ground? If the energy was going through the air, he could have waved that light bulb in the air, right? Just excite the gases in it. He could have taken the magnetism that's coming off of the Tesla coil and got the energy out of it, right? Because that's probably the most efficient way, most people would think. But it's not. Not at all. You see, you need to change that energy, but you need to break it as well. Energy sometimes is about breaking in transformers. So when you want to get some more energy out of this thing, put the rod in the ground, put the energy through the ground. Now we have electrical transference through the ground with an energy that's not killing you. That's really what he did. That's it. When he goes to ping the ether, why is he able to ping the ether? Well, when you start using water as your ground, guess what? Let's start pinging the world. But what does it also do to your Tesla coil? If you resonate at 300 kilohertz on your Tesla coil, putting a rod in it will change the capacitance of your Tesla coil. You can now resonate in the hertz. Not kilohertz, hertz. You can now lower the frequency of your Tesla coil. The earth works on hertz. It's not working on kilohertz. We produce kilohertz for what we want to do. The earth works on hertz. You take people on a bridge. Too many people on a bridge. They're not creating kilohertz. We don't have a bunch of Flash Gordons out there running on the bridge. We're not hauling butt. No, that's not us. We're moving slow. Thump, 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 thump. Hertz frequency. That's what the earth works on. When you disturb that frequency with so many people together, you get resonance. When you get resonance in that frequency, it starts to mess with the bridge. It sways it. It tears it down. Why? Because you're becoming resonant with the earth. Now, for what I do, why is this so important? I'm creating a pump to the ether, to the earth in my Gravity Flyer project. That's the point. Tesla was pinging the earth by putting the rod down the center. Now mine's a little different. I'm going to my Gravity Flyer, but my Gravity Flyer's on the ground. You see, it is the grounding. It is the rod going into the ground. I simply put a wire to it and change where I'm doing it. Okay? I'm changing the locality of it. I didn't change what it did. I just changed where I put it. Now, in order to get the ether, I need to ping it. That's what Tesla was doing. He was pumping it and pinging it. Ping, ping, ping. It goes, it goes, it goes. It comes up in energy spikes. That's what it is. We're filling this Gravity Flyer with ether. When you create the bubble of the Tesla coil field, what is it doing? It holds it in. Why? Because it's holding in the original. It held in the original that came in the center of the Tesla coil. So now when you're producing this thing in a Gravity Flyer, you're pumping the energy into it. That's the key. That's how I understand it. That's why I understand it. Because these are the tests you have to do. So when you start pumping that in there, you're now getting rid of everything else in there. Now you have a gravity flyer with a field on the outside and ether on the inside. It's exactly what you wanted. You now have the ability to lift. That's the key. One of the greatest things Tesla ever did with this. So why can you touch it? Because it's broken. It breaks the energy. It's not directly tied to your Tesla coil at all. There's no wires connected here. This is a rod down the center. There's no extra wires connected. The number 2 wire does not connect to it. It simply goes down the center of it. That's the understanding of it. You're pulling an ether energy out. So when we start looking at coils and stuff, we've been looking at a lot of coils on this channel. Why? Because the center produces an ether. So the coil tells you how it's producing the ether. The gravity flyer uses the ether. That's the difference. But to produce the ether, what do you have to have? You have to create cold in the center, heat on the outside. Energy must flow. It must go out of the outside and have a breakout. It must then flow to the center and get condensed. The concentration of energy in the center is going to be higher. Everybody says, well, there's Tesla involved right there. The actual meter Tesla is what I mean. When you put it in there, you get a higher magnetic field. But what's actually going on more than that is you're getting ether inside. It's the cooling of that material. So now, what are you doing? You're taking a conductor and you're taking part of it and you're making it a superconductor in the center. The lower you can get that amount right there of temperature, the better you are, the more this coil works. That's why. You want to do that in a coil, you have to use geometry to get it there. The flow, where it pings at, where it's going to, what it's hitting, what values are increasing. Those are numbers you're going to have to work out in mathematics in order to get it right. But the one thing's very evident. You're going to have to make resonance in it. It's going to have to feel like it has a Tesla coil in it in order to produce the field on the inside. In order to get that ether to form, you have to do this. If you do not do this, it will not work. That's why we look at the coils, guys. They are producing something that we're not getting out of everything else. We have now changed a Tesla coil into a coil, but we've added to it. We have now added where we can get breakout out of it. That's the thing. You have to have that in that coil. That breakout's important. Now, do we try to cover it up? Yeah. Why are we covering it up? Why are we putting epoxy in there? You know why? Do you really want to know why? The whole reason you put these things in epoxy is so that you can change the energy form that comes out. You say, okay, maybe I want static to come out. Maybe I want scalar to come out. Well, you can't get those changes in a coil because it's all connected together without that epoxy. That's kind of the thing. You're going to get a low budget version if you don't put it in epoxy. And the low budget version isn't anything like the best one. Not even close. So that's why you do it. You need that breakout to change the form of energy coming out. But you'd never know it if you didn't deal with the temperature transference of the energy. You see, distance matters. So when you go to set up high voltage, you put two pieces of the anode and cathode across from each other. You put them too close, they spark. You pull them a little bit further out, what do you get? You get the energy that transfers over in plasma. What do you want? You don't want to go this far out, okay? When you're doing this, you're just getting straight charge. The inside of it, just a little bit's a scalar wave. You see, charge is what they use on high voltage line. In between the two high voltage lines, you're getting a massive amount of charge. Now, Steinmetz turned around and called this the dielectric. It's a field of energy. We generally think of a dielectric as plastic in between our two coils as a divider. But that's not what Steinmetz said it was. Steinmetz continues to tell you it's a field. If you follow that, then between two high voltage lines, you're going to get a field. Now, whether it goes in electric statics, whether it goes in scalar, whether it goes up to plasma, or it goes to a spark, it all depends on the distance. They have anti-sway on every one of these because of that. They do not want to change the distance. Okay? Now, we all are sitting there getting this, okay? Now you have to understand your project, okay? We have to really start to understand this, guys. When we start working on these things, the correct principles have to be there. We cannot do this stuff without them. If you do not understand the temperature transference, your project is going to suck. Okay? You're going to get energy spikes. You're going to get unwanted heat because you didn't account for it in the beginning. You have to start cooling down your projects when you do them and keep the room the same temperature. This is why labs do this. We don't do it out in the sun. We don't do it when a garage is hot one day and cold the next and expect the same thing. You have to take that temperature into account. Now, is it easier to see it in high voltage than low voltage? Absolutely. Yeah, high voltage tells you the answer. It correctly tells you the answer. It tells you where it wants to flow. It tells you when to do something and when not to do something because it's an immediate response. For every kid these days, man, it's exactly what they wanted. Hey, turn it on and it works. Forget about how we did it, but turn it on and it works. Instant gratification, right? That's what high voltage gives you. Now, transfer your knowledge into low voltage and start to understand this point. When you're dealing in coils, the voltage is really low. But that's okay because they deal in resonance. They are not trying to overvolt this thing. You are not overpowering it. You are putting in a relatively low voltage, but your frequencies are going to start to hit. You're going to get a frequency on the outside of the coil and a frequency on the inside of your coil. They're going to resonate together. The frequency on the inside of the coil will probably drop. That's how you know you've reached the resonance in that coil. It's very interesting to understand this. Now it starts to make sense, doesn't it? It starts to clear up a little bit. It starts to get there, okay? And we start to understand this, okay? We're getting a bigger picture here, okay? We're starting to really produce something great, okay? Now, I'd love to be able to sit here and tell you it's a different way, but every test that I've done says it works this way. Every one of them. And guys, I don't like messing around. I don't like to play with things and have them wrong. I like to get them right, okay? And I spend a lot of times going over things and moving things around and trying them different ways to get it. As far as I know, I'm the only guy on this gravity flyer that's run this thing this many times and come up with this many answers on this thing about every little process that goes on. Now, I've seen Jared do a lot on this thing. Don't get me wrong. That's not what I'm trying to say here. But what I am trying to say is when I'm finding the ether, nobody else is, and I understand why you put the magnets in there the way you do, and you don't heat up the center because you're working with cold voltage, and all you're doing is wasting it, then I know I'm probably the only one. And it makes it hard to say this to people because they're in a whole different area of understanding of this, okay? We're so far apart at this point that in order for us to get back together, we would have to do the project together to see it the right way together. That's it, okay? So, guys, I don't have a lot of time today. My son has to go, or else I'd bring people on and share the videos they have. Trust me, I really want to. Maybe I'll come back later as soon as I'm done dropping them off and do it. But I just wanted to get this point out there to people because I think they need to understand it. We're working in a different system that you think we are, and it's about time we fix that system. We go back to the beginning, look at the volts and amps, and we get the right thing. We deal with the temperature transference, and get rid of the letter that was representing it, because it's a variable thing. It will change as your project changes. What does that mean for our projects in the end when we fix it? Now we're going to get towards a superconductor with these coils. That's what it means. And there's a reason for it. Okay, now you can apply a reason to it. Now when you write out your physics equations, now you can start to see the relationship. Now you can fix it properly. Okay, that's what's going on here. There's a means to the end. We've figured it out the right way. Now, when everybody catches up, the physics equations are going to have a basis in reality. We're not having a basis in the middle of nowhere. We don't have a volume of liquid when we're dealing with energy. We have energy. Energy transforms. It's heat, it's voltage, it's amps, it's all of it. Frequency is the main driver of whether it goes to voltage or it goes to amps. That's it. That's as simple as it gets. If you can control your system, you can control it. We have Amazon parts that you can buy for under $20 and put it on your flyback transformer and control it. That's it. You just take a trigger circuit, you go around and you take a frequency generator and then just make sure it has a duty cycle on it. And guess what? You can now control energy. That's about as simple as it comes. I've done it. I've done it a lot. I do it all the time. Why? Because I cannot have the same energy going in and worry about, does it come from the wall? Does it come from a battery? Does it come from a different country? No, I don't care. I'm changing it anyway. I'm going to manipulate everything. Now I can get the right result because I knew how to change it. That's kind of what I'm trying to tell you guys. Look at what you're doing. Looking at your successes and failures in this and see why they're happening. Once you get that, then you're good. You're going to do a lot more. Resonance is far more powerful than any voltage that we put into any of these things. Okay? It is the one thing that's misunderstood in this world. And when you finally get it, when you finally understand it, you're going to start to see why. We can now transfer things easily. Now we don't need the wires as much as we used to. We can now do it through the air. Energy transference through the air was the goal of Tesla. He knew how to do it. He just needed funding. We now have more tools to our disposal where we can start doing it on a smaller scale and then turn around and get this thing to the right level. That's my goal here, okay? I have a gravity flyer I need to lift. I found out the way to do it. Okay, I'm getting good results with it. I want everybody else to succeed. I want the Tesla coils to succeed. I want the coils to succeed. I want them all to succeed together. I will hold back my project until some of these other ones get to that point. And that's where I'm at. Okay? I don't have to show my results right away. What I do have to do is make sure everybody gets up there so that we do not have it turned away by a bunch of scientists who are using the wrong equation. That's the thing. Okay? We just have to put it together as one. Then when we have a full picture, we have the right answer. So either you can work towards that goal or you can work against it. That's your choice. I'm going to work towards it. And every day that I do it, every project that I put into it, every understanding I get and give to you guys, it's so that we can all get there together. Okay? I just don't want anybody's schooling or education or, hey, I'm working with a university or I have to do this and get my stuff in this line. I don't want to hear all that. I want to hear we're all here for the betterment of everything. And then we all trade notes and we get there. I'm right now trading my notes. I'm giving them to you. There's a lot of stuff in here, man, that if you simply follow what I'm saying, you're going to get a lot further ahead. You got to stop looking at, I need the big picture right away and start looking at the small picture and rebuild it the right way. Please do it. I ask you, I beg you to please try to fix it. Okay? We need these things to fix so that we can get the right answers from the mathematicians. They work the numbers, but they only work the numbers that you give them. Now it's time to add the right formula to get them to the right number. Then we all succeed. Okay? I'm not here to have anybody else fails. I'm here to everybody to succeed. Okay? That's the thing. Okay? So you want to come on to the next live stream? Absolutely. And I'm sorry, Jeremiah. I will absolutely have you on. If I come back later today, I will send you a message on it. But absolutely, I will bring you on. Okay? And we'll do this again. Open source is the key, guys. Yes. I hope you guys learned something today. I hope you guys rethink your projects. Any successes, failures, let me know. I'll help you. I have no problem. I don't have an ego in this, guys. I really don't. I just want people to be able to get to the same point at the same time so that we can all share. Okay? That's it. So anyway, thank you guys. And if I come back later today, I'll let you guys know and we can all get on here. And then absolutely, I will start sending messages to people and invite them on and do this with me. But I have to go take my son right now, or else I would do it right now. Anyway, guys, thanks for listening to me, and hopefully you guys learned some things. So have a great day, and hopefully I'll see you guys a little later, and I'll come back.